video, we're going to continue with looking at these 7 problems that hopefully you worked after watching the last video before you started this one. If not, I encourage you to pause the video, write these 7 problems down, work them out, and then check your work with what we're getting ready to do. Okay, so here are the solutions. Okay, first of all, let's take a look here. Sine of pi x dx. Well, sine of pi x is certainly not one of our basic rules, but with the simple substitution we could get it to be there. Be one of them if we let just u be pi x. Well, if u is pi x, then du is pi times dx. Well, if we put a pi and the dx together, that becomes du. But where'd that pi come from? Well, we just stuck it in there, but if we're going to do that, we have to balance it by putting a 1 over pi out front. Technically, we're putting the 1 over pi here and then moving it out front. Since it is a constant, that's a legal move. So this equals 1 over pi times the antiderivative of sine of, that pi x becomes u, and the pi times dx altogether becomes du. Okay, that's something we know the antiderivative of. It's minus 1 over pi times cosine of u, and when our last integral sign disappears, it's c. So the derivative of cosine is minus sine, so the antiderivative of sine is minus cosine. And, of course, then we finally substitute back in u equals pi x, and we get this. If we were to check this, notice you're checking it with exactly the same substitution. You're taking the derivative of this with respect to x. The first thing you do is this constant multiple rule, is minus 1 over pi. And then you do a substitution where u is pi x. The same substitution. The derivative of cosine is minus sine, so it's minus sine of u, so that makes this plus 1 over pi. And then we have sine of u. And then we have the derivative of the u, but the derivative of the u is the pi, which cancels that 1 over pi, and when it's all said and done, we're back at sine of pi x where we started, so it does check out. So notice that what we get here is an entire family of antiderivatives. So if we take y equals this formula for different values of c, we get these various different graphs here. This, of course, these are only part of them. There's one of these for every possible value of c. And I believe this one down here is c equals negative 10. This was negative 8 for c, negative 6, negative 4, negative 2. 0, 2, 4, 6, 8, and 10 for the values of c. And of course what you get is each one of these is a function and they're vertical shifts of each other. So we get an entire family of antiderivatives. Okay, let's look at the next one here. This is a definite integral, so ultimately we're going to get a number. It turns out to be 2. And that represents an area that you see here. So we're integrating from 0 to pi. Turns out to be 2. First of all, let's just see if that makes sense. It is going to be a positive number. All right. If you went up a rectangle here from 0 to 1 and you went over to pi, that rectangle would have an area of pi, which is just a little bigger than 3. And it looks like we're around 2/3 of that rectangle filled in. So 2 seems like a reasonable number. Let's go ahead and work it out. This one, we can find an antiderivative directly, no substitution required. So the antiderivative of sine x is the opposite of cosine x, and we evaluate from 0 to pi, which means you plug in the pi and the 0 with the subtraction right here from the fundamental theorem, and we put a negative here and here. 2 negatives make a positive here. Cosine of 0 is 1. Cosine of pi is negative 1, and these 2 negatives make a positive, so we have positive 1 plus positive 1 is 2. By the way, before we ever started this, we should have made sure that the sine of x is actually continuous on this interval from 0 to pi. And of course, sine of x is continuous everywhere, so this is certainly a legitimate process. You could check this by running this through your calculator and doing the numerical integration technique on your calculator, and it should come out with at least approximately 2. Okay, let's look at the next one here. Oh, that looks like a lot messier situation here. Now, first of all, the basic kind of problem is we're looking for the formula for f of x, and this time f of x is a specific function. We know its derivative, and we know one point on it. So it's a specific antiderivative of the given function f prime of x, which equals 4 e to the x cosine of pi over 2 e to the x. So let's work through this. Well, that looks kind of messy. We need to find an antiderivative. Well, notice you have cosine of something, and that something is kind of complicated. Let u be that something inside the parentheses there, that argument or their input for the cosine function. So we let u be pi over 2 e to the x. We'll see if this works. In general, substitution is somewhat of an art as well as a science. It's kind of a you have to learn certain techniques that work, and then you also have to sometimes just guess and check. And so we try something to see if it works. If it doesn't work, maybe try something else. In this case, if we let u be pi over 2 e to the x, when we take the derivative to get du, we first use the constant multiple rule, so that gives us pi over 2, times the derivative of e to the x. Well, the derivative of e to the x is e to the x, and of course du always has the dx with it as well. Well, that works out okay. There's the dx. Here's the e to the x, and we can stick in a pi over 2 as long as we put a 2 over pi out front. So that's accounted for. Here's our cosine of pi over 2 e to the x. And I put the 4 out front with the 2 over pi, so 4 times 2 over pi is 8 over pi. So it gives us 8 over pi out front. The integral of this becomes cosine of u, and this part in parentheses becomes du. We know an antiderivative there. The antiderivative of cosine u is sine u. Derivative of sine u is cosine u. So this, we still got our 8 over pi, and we still got our plus c. Now this time, we go ahead and substitute in the u, which is pi over 2 e to the x. But this time the c is not an arbitrary c, but a specific c, because we have a specific number, ordered pair, input, output pair, input 0, output 3 over pi for this function. Any function that looks like this for any value c will have the derivative that we want. But we can find a specific c if we plug in this particular point. So we plug in 0 for the x, we plug in 3 over pi for the f of x, for the output, the y. Now just solve this equation for c. E to the 0 is 1, so we got sine of pi over 2. Pi over 2 is 1, so 1 times 8 over pi is 8 over pi. Subtract 8 over pi and you get negative 5 over pi. From both sides you get negative 5 over pi equals c. Plug that back in place of c right here, and so we get this line here with the right thing in place of c. And we see the function we're looking for is 8 over pi times sine of pi over 2 e to the x minus 5 over pi. Now, if we wanted to check this, we would need to check two things. First of all, we need to check that if we plug in 0 for x, we do get 3 over pi for y. And we want to check to make sure that the derivative of that is the function that we started with. Now, what we're looking at is a specific function, which you see graphed here in blue, and its derivative is graphed in red. So you can check that. And then also, it's kind of hard to see here perhaps, but I actually plotted a point right here at 0 pi over 3 over pi, excuse me, which is that point right there. And sure enough, that is on the graph. Okay, a couple more here. Okay, this is another family of antiderivatives problem, or in other words, an indefinite integral problem. Again, we have something that's kind of messy here, but if you see the same thing inside these trig functions, one thing to try, may not be the only thing that works, or might not work in some cases, but one thing to try is to let u be x squared. And if u is x squared, du is, this is supposed to say 2x dx. I've got it here, so I'll just copy it. So du is 2x dx. Okay, right here. And so if I put 2x dx here, that becomes du. Now, if you look at the original, there's the x, there's the dx. I just stuck in the 2, but I balanced it with the 1/2 out front. I got the 3 out front as well, getting it out of our way. 3 times 1/2 is 3/2. And the rest of it's just like it is. Now we can substitute in u equals x squared here and here, and 2x dx altogether becomes du. Now that still may look a little bit messy until you remember that the derivative of secant u is secant u times tangent u, so this actually is one of our basic properties. So this is 3/2 secant of u plus c. Once the integral sign disappears, you put a plus c at the end. And then we just substitute back in u is x squared, so this is 3/2 secant of x squared plus c. And here we see it for different values of c. You can see about 1, 2, 3, 4, part of the 5th one, maybe part of the 6th one down here. So you can see certain values of certain graphs of the function there. That's for certain values of c, and so you get these family of functions, all of which have the same derivative, and the derivative being this what we started with, 3x secant of x squared times tangent of x squared is the derivative. And the function we're looking for, the family of antiderivatives, are these green graphs. This is some of them. So I've overlaid several of them, and notice they're just vertical shifts of each other. So we get a family of antiderivatives. Okay, let's look at the next one here. Well, again, we're kind of starting to see a pattern where we let u be the part inside the parentheses on a trig function if it's more complicated. So we could let u be pi x, then du becomes just pi dx. Well, we can certainly stick a pi with our dx to make du as long as we balance it with the 1 over pi out front. And then this becomes secant square of u du. Now remember, at the point that you switch from x's to u's, these limits need to be either you need to change them to the appropriate u values, or you just need to indicate that they are x values. I usually choose the route where I just say x equals here on the limits, so I'll know that those limits are not u values, which would be indicated by this du here, but rather they're x values. Now the antiderivative of secant square u is tangent u. Remember, the derivative of tangent u is secant square u. So you got to get those derivative rules down so that you can turn around and do them backwards for the antiderivatives. Now we still have our 1 over pi. We're going to evaluate from x equals 0 to 1/4. So we're going to switch back to x's by substituting in u equals pi of x, pi times x. I also noticed that each one of these is times 1 over pi. This is actually 1 over pi times tangent of pi times x, where x is 1/4, minus 1 over pi times tangent of pi times x, where x is 0. They both have the 1 over pi, so I can factor that out using the distributive property, as you can see down here. So I'm going to bring that out front. Then I just plug in the 1/4 and the 0 and work it out. Let's do this one on the right first. 0 times pi is 0. That's easy. Tangent 0 is also 0. And when I plug in 1/4 here, I get pi over 4. Tangent of pi over 4 is just 1. 1 minus 0 is 1. Times 1 over pi is 1 over pi. And so we get, this gets an actual number, which is 1 over pi. We should be able to visualize that as an area. And so the purple graph here is the original graph, secant square of pi times x. And I'm going to integrate it from 0 to 0.25, which is 1/4. And the area of this region that you see, so it has a curved top and then straights on the bottom and the sides. And that area turns out to be exactly 1 over pi. Okay, let's take a look at this one here. This one we're looking for a specific antiderivative where we're given the formula for the derivative and a point on the graph. So f prime of x is 1 over pi times x squared plus 1. So the f of x is a specific antiderivative there. I can bring the 1 over pi out front, and this is 1 over x squared plus 1, which is exactly the derivative of arctangent of x, or inverse tangent of x. Now I still have my 1 over pi out front, but if you take the derivative of arctangent of x, you do get 1 over x squared plus 1. Now I need my plus c, but this time instead of being an arbitrary c, I'll be able to find its value by plugging in 1 for x and 5 for y here and here. Now arctangent of 1 is pi over 4. The 1 over pi is going to cancel the pi, so this is 1/4. Subtract 1/4 from both sides. 5 minus 1/4, or 20/4 minus 1/4 is 19/4 equals c. And so f of x is 1 over pi times the arctangent of x plus 19/4. You might write that as tangent and then -1 superscript x, as well as it is written on your calculator. Now here I have the original f of x that we're looking for. Our final answer is in blue here. You can see it graphed 1 over pi arctangent of x plus 19/4. And it should go through this point that we talked about, 1, 5. Where's 1, 5? 1, 5. Yeah, I got a little dot there, see it? So it does, in fact, go through 1, 5. That's good news. And then the derivative is down here. Notice this function is increasing here, so it's increasing everywhere. The derivative is always positive. It goes from concave up to concave down with an inflection point here at when x is 0, so that's going to be your maximum right here on the derivative. And the formula for that derivative is the original function up here, 1 over pi times x squared plus 1. And you can check that by hand or with technology. Another family of antiderivatives. Here we have the antiderivative of 4 over the square root of 1 minus 4x squared. Now this one's a little trickier, substitution. We might try, things to try. Probably the first thing I would try is to let u be 1 minus 4x squared. Then du is going to be negative 8x dx. Well, the negative 8's not a problem. The dx, of course, is always there. But that x gives us a problem. Had there been an x on the top, that's exactly the substitution we would have used. But the x is not there, so we need to look for another alternative. And it might take a little bit of experimenting to find this, but if we let u be 2x, then du is 2 dx. So certainly we can put a 2 here. We put a 1/2 out front, put the 4 out there with it. 4 times a half is 2. So that 2 times 2 is 4, back where we started. And then the thing to watch is that 4x squared is 2x squared. So then when we do our substitution, this becomes 1 over the square root of 1 minus u squared du, that we take the antiderivative of. We got the 2 out front. Now that's okay, that's pretty good, because that's actually the antiderivative of arc sine of u. The derivative of arc sine of u is 1 over the square root of 1 minus u squared. So that works out pretty nicely. Substitute back in the x. We get 2 arc sine of 2x, and of course you always have the plus c at the end. Now if you graph these for different values of c, I've got certain ones graphed here, you get these vertical shifts of each other, which are these blue graphs. But they all have the same derivative, which is this red graph here, which is the y equals this original function, 4 over square root of 1 minus 4x squared. Okay, and I think that got us through those basic ones. And we'll review some integration formulas again here in the next video.